Thank you. And yes, hello everybody, I'm Ulrich, and well, a lot of you know me from Internet Stiftelsen, and the rest of you will know me from ICANN now. Good. Yes, today's topic is DNS and the quantum computing, and well, let's start with a little disclaimer here. If you don't know Richard Feynman, then we can agree that we both know exactly as much about quantum physics, nothing. Well, everything I'm going to present today it's not my own research, it's not even my own papers. There's researchers that have done papers and overviews over the state of quantum crypto, quantum computing, and that's what I'm referring here today. There's a white paper from ICANN, and I give you references in the end, but that's what I'm going to talk about today. So no questions on quantum physics. I have absolutely no idea. Okay. So the first thing we need to talk about is crypto-relevant quantum computers. Okay, and what is that? Now, if you think of, say, you all have heard about that, quantum computers will break encryption. And surely there is the possibility of that. But not today. So today we're in a stage when, let's say I would tell you, I have a perfect password breaker. It can break all passwords with 2 or 3 letters. Great, but nobody will have sleepless nights over this. And that's approximately the state that quantum computers in today. The factoring that they're doing for RSA, the highest number they factored right now is 35. I think everybody of you can do that. Much easier than building a quantum computer. So it's, the state is very limited right now, but it will get better. And one more thing is, we have heard today about Shor's algorithm, and it is said that Shor's algorithm will break quantum public cryptography, and that is certainly true. But when I heard it the first time, what my idea was that, well, you run this Shor's algorithm on a quantum computer, and out comes the private key. That's not what it does. So in information science, you have this theory of complexity. And so if you run an algorithm, then you have the first one is like constant. Every time you run it, it takes the same time. Then linear. If you have more data, it takes more time as the data grows, time grows. Then you have exponent. Then you have a polynomial growth, and then you have exponential growth. And exponential growth is that what we have today with public key cryptography. A longer key, and suddenly, it will take millions of years to factor these numbers. But what Shor's algorithm does, it will reduce the complexity to polynomial time. So it means that you will have a quantum computer, and behind the quantum computer we'll have a supercomputer, and the supercomputer will compute the private key for you. So it's not that we are in the close to, we will have this on our desk. And how far away from it, we will look in the next slide. So there's a lot of stuff going on in this slide. First let me point out that the axis, x and y axis, are both logarithmic. And then on the y-axis we have the error rate. As we get higher on the axis, the error rate gets lower, right? Okay. And on the x-axis we have the qubits. And well, you would say in the right upper corner you have the perfect quantum computer that has almost no errors and huge amount of qubits. And in the lower corner, left corner, you have quantum computers that have lots of errors and very few qubits. And well, if you look at the gray area, that is where today's quantum computers are. And then we have these red lines. And the red lines is RSA algorithm with different key lengths. And then you can see what is needed, where a quantum computer needs to be to break that algorithm. And so even if you reading this graph very, very kindly, you realize that it's a factor of at least 10,000 times that quantum computers need to improve to be able to break RSA. And, well, 10,000, that is approximately 2 to the power of 13, something like that. So if quantum computers would improve like in Moore's law, double the number of transistors every other year, that would be 26 years from now, okay? So, so researchers are very, very sure of a prediction that there will be no quantum computer that can break public key cryptography in the next decade. No, they can, obviously there can be breakthroughs, but it's unlikely that a breakthrough would be so big that it would shave away everything of this. Okay, so that is then the question is, okay, so why are we talking about this? And of course, that is in crypto, you have encryption, and certain people have needs to keep things secret for a very long time, right? I mean, if your transaction with Amazon probably don't need to be secure the next 50 years, so we don't need that really. But Sweden's defense, yeah, we probably want a lot of this to be even a secret longer than 50 years. So that's why people are talking about this, okay? And then when we look at the DNS obviously is a request-response protocol. So, I mean, we are not concerned. DNSSEC uses obviously public key cryptography. So if a quantum computer could break it, it could break DNSSEC. Would be really bad. But obviously, we are not concerned about breaking it 10 years from now. I mean, I get the answer now, and now I'm really sure that it's not broken. So I don't care that, 10 years from now you can send me a wrong answer. Okay, that's so. But crypto agility, it took us 5 years to roll the root key, and then we didn't even change algorithms. Only thing we did was change the key. So think of, we need to change the algorithm, and we don't just need to change the algorithm in the root, we need to change it in all TLDs and all second-level domains, so in all resolvers. So, and you realize that, well, that's a decade suddenly is a very short time. So that is why we're looking into this today. And yes, DNSSEC. So we need to, so what do we do with DNSSEC? And well, the problem with today's quantum algorithms is that they are, most of the keys and signatures are very large. So, and there's actually researchers in Germany, Niels Visiol and some more that have looked into this. And this is a table from Moritz Müller. And you can see here there's different post-quantum cryptography algorithms. And what you can see is how large are the public key and how large are the signatures. And you see some of them are not so bad, and some of them are really, really bad. I think the rainbow one is already broken. This is a little bit older table. So, but what we can see in this is that we have to be very careful in finding the right algorithm, because DNS is very sensitive of packet sizes, right? So we need to look into how do we manage this. And then there's the question of how fast can we sign, how fast can we validate. And especially the validation part is important for ISPs, because I mean, if you have 1 million customers, you don't want to have 1 million servers for them. You just you ideally only one. And so, but what we see here, if you look at the table, that signing, we will look more into this Falcon algorithm. It's one of the best bets we have for DNS right now. and you see that the signing is actually faster than RSA is. The validation is slower, but it's still faster than ECDSA, which is the most used algorithm in DNSSEC today. So, not so bad as an algorithm as it goes. And the size of the signature obviously is, I think it's 660 bytes exactly. So, not good, but it's still manageable in one UDP packet. And let's see here, yes. So, packet sizes. There's, as I said, the researchers in Germany, they actually made a proof of concept implementation of this. They signed a zone with the Falcon algorithm, and then they did run a resolver who was validating this, and they requested different domains and then different types of records and looked at how big are the packet sizes. And as you can see here, the A and quad A records, the packet sizes is 800 bytes. That's totally okay, not a problem. But then if we come to NSEC, so non-existent names, suddenly the size really goes up because the NSEC record is big, the signature is big, maybe you even need a wildcard, so it gets really, and then we come to sizes that are actually, that gets fragmented. And nobody on the internet likes fragmentation. So, and then we go to TCP, and TCP is in DNS is a problem in itself again. So we have to see how bad this really is and what we can do about it. Okay. So, this year they actually made a new test, and in this test, what they actually did is that they used different algorithms, signed zones with it, but exposed it to the internet, and then made requests to the RIPE Atlas network, and looked at how do we get back correct answers. And so the first thing you can see is that for RSA SHA-256, they got 100% correct answers, and that is expected because they selected the probes after giving correct answers for that algorithm. So that's a pre-selection. So, so you can see that, see there's TCP. Yes, so the upper two graphs are UDP, the lower two are TCP, and you have to the left side request without the DO bit, so no DNSSEC information, and to the right side with the DO bit, so request additional DNSSEC information. And as you can see, most of the answers weren't that bad. I mean, if we go down the list, it gets a little bit worse at the end, but that is the last two algorithms actually have signatures around 30 kilobytes or something. So there's, not something that you see very often, and that is DNS is, really suitable to transport over UDP. Yes. So, but what you can see if you look at the Falcon algorithm is that it's actually doing, not so bad. So there's at least hope. Let's put it that way. And so but then we go to the negative answers. So in this graph, again, UDP on the upper two graphs, TCP on the lower graphs. So it's not that the algorithms has doubled here, but if you see this where it says RSA SHA-256-3, we have answers with NSEG and with NSEG3. So clear text answers, hashed proof of non-existence. So, and you can see that the quality of the answers differs a little bit depending on what you do, but I mean, what we definitely see is if you look at the last algorithms, that the signatures are so big that, we don't get anything for it. It's like half of it just falls away, and that is because of the signatures are so big. And if the data gets over 64 kilobytes, DNS doesn't know how to transport it, not even over TCP. So, but again, if you look at the Falcon algorithm, it fares quite well. So, yeah, and ICANN has written a white paper on this. We have that on our website. We have two conclusions of this. The first one is the community doesn't need to do anything yet. And that is basically because there's not enough standards, there's not enough research into this, there's a lot more work we need to do before the community really can, starting to decide how do we change the root key, how do we, manage all of this. There's a lot of stuff to do, but right now we don't have the basics in place, and we need to wait for this to get into place. Yes, and then there we have this little part of the DNS that actually uses transport encryption. So we have DNS over TLS, DNS over HTTPS, and soon we have DNS over QUIC. But they are all dependent on TLS. And so the recommendation is do what the TLS people do, right? So, and what do the TLS people do? Well, there's a lot of work in the IRTF, the Internet Research Task Force, which is associated to the IETF, the Internet Engineering Task Force. And the IRTF has a crypto forum where they talk about crypto algorithms and what could be standardized into protocols. And at the IETF, there's a working group that just tracks all the quantum stuff that's going on in the IETF, if you're interested, to see what is going on in protocols, okay? And yes, then there's a little reference here. We have, as I said, the white paper from ICANN, Octo 031. Then the ICANN Security and Stability Advisory Committee has had just a workshop where they had a presentation on this and discussed this. And well, if you're interested further in this, we have Netnod has their very own member of this group, Patrick Feldström, and he knows exactly more about this. And yeah, and then there is a reference to the German research if you're interested in more data. Okay, and with that, say thank you. And,